Yeah, yes, sir.
Yeah, with your kind permission, shall we start?
Just sir,
Yes,
give
sir.
me
Yes,
1 minute. I am just starting a YouTube live
Okay,
so
okay.
that you.
Secretary Shashikant Shinde, sir, and Havaldar ma'am, please start your videos, cameras.
yes, sir.
हाँ
I
गुड
started.
इवनिंग मानेश सर नमस्कार कन्वर्ट मनीषा
Namaskar to
मैडम यू
everyone.
कैन yes you can start now
Yes, sir.
Good
Yes, sir.
evening.
Good
good
evening,
evening
sir.
Good evening. Good evening, everyone. On behalf of IIPT-RC Pune-08C, I am inviting Vandana Luthra, Madam, the respected speaker today.
Thank
In
you so
spite of
much.
a very day, thank you so much, ma'am, that you could
Thanks a
help
lot.
us.
Thanks a lot.
Be sure that your lecture will be outstanding and we will all love it. And
Thank you.
henceforth, I am transferring these things to Dr. Kangude, sir. I am inviting him to introduce you. Thank you.
Okay,
It
okay,
can be a
okay,
short
okay.
introduction only. So
Yes, very,
then,
very, very short, very short. Just few minutes. Yeah. Thank you, ma'am. Uh, it is my great privilege to introduce Professor Vandana Luthra, ma'am, of the Department of Physics at Gargi College. At present, she is acting principal of the same college. An accomplished scholar, she has pursued uh, advanced research internationally through prestigious fellowships at University College London and the State University of New York. At Gargi College, she has established a vibrant research laboratory guiding numerous PhD and undergraduate students to academic success. Her excellence is recognized through awards like the Meritorious Teacher Award and the IAPT Deenbandhu Shahu Memorial Award. Professor Litra has led several funded research and innovation projects, including an international UKI-ERI partnership on nanotechnology. A dedicated educator, she has trained hundreds of teachers in innovative pedagogical tools and champions active learning in physics. Her scholarly contributions include over 38 publications, and she actively serves as a reviewer and conference speaker. Beyond academia, this is a very important aspect of her character. Beyond academia, she promotes an environmental awareness and has contributed educational resources on climate change. Professor Luthra is also a master trainer, a poet, a very rare combination, physicist and poet, and passionate advocate for demystifying complex sciences like quantum computing for learners of all ages. We are very thankful for her at a very 11th hour, just very with a very short notice. She agreed to deliver the session today, and that's why IIPT RC08C very kindly helped. So I request Vanda ma'am to please go ahead and start her session. Thank you.
so first of all, thank you so much, and I'm honored by the presence of Professor Joy Ghatak, Rekha ma'am, and all the office bearers of RC Pune, as well as Sub RC Pune, and everyone, all the participants, and for your gracious presence. And I will try to give some glimpses of this because in limited time, whatsoever best I can do, I will try to do. So please, I'm going to share my screen. Please allow me for that, and looking forward to having useful interaction with everyone. So let me share the screen. Is my screen visible now?
Yes, madam.
Yes, ma'am.
Okay, okay. So I can start sharing in the slideshow.
Yes.
Yes, is it visible in the full screen mode?
Yes, madam.
Okay.
Yes, it
So,
is.
knowing about the diverse, say, background of the speakers, this talk is going to be as a pedagogical tool as well as catering to all sorts of audience which we have. I am told that there are school students also, there are undergraduate students, there are very learned, experienced speakers also. So I will try to make it as simple as possible so that everyone is able to understand and carry forward the message which is being conveyed through this talk. According to this talk, it also means that the quantum technologies are difficult to understand, but that will not stop the disruption this set of emerging technologies will bring in next few years. And we are seeing, witnessing a phenomenal change, the way these are being looked at and the revolution these are bringing. This is by Kevin Coleman, and but these words of Albert Einstein's are always say motivating, that I have no special talent, but I am only passionately curious, and that is something which drives to learn about new things which are happening in the current areas. And the motivation of the talk is also going to be that these are having diversifying in nature, and in this case the understanding of the very basic qubits and quantum gates is fundamental in understanding all these quantum computings. There is a, according to the National Quantum Mission, 6,000 crore plus has been committed by government, and in that it is underway, all these things are underway in four different verticals. Those four different verticals are being practiced, are being implemented across the country, and there is a eureka time for the students, because these kind of opportunities, if they are trying to understand the vocabulary, to understanding of the functioning of these basic concepts to applications, that will actually help the students also to explore beyond the domains in which they are learning. And in this, I will be talking about IBM Quantum Composer and also how these gates and circuits are demonstrated using Qiskit. A small demo will be there. Other than that, I would like to also mention here that quantum computing is an interdisciplinary field. Other than physics, it also needs foundational background of mathematics, electronics, nanoscience and nanotechnology, computer science, engineering, and especially cryogenics, which is low temperature physics, because many functioning of the qubits requires working at a very low temperature in the Kelvin range or sub-Kelvin range also. And it also requires knowledge of material sciences, because the materials which are being utilized for different applications also are based on the fundamental properties of the material sciences. And physics being playing also plays a very important role in this, because the quantum mechanics which we now know has matured for last 100 years is also finding its own its basis in applications which are emerging out of it. So this is a motivation that other than physics, other interdisciplinary fields are also included in this. And when we talk about the physics, the most important thing to understand here is that the central universities and the state universities are still not having or are still not offering this kind of paper, which is otherwise there in, say, IITs, ISERs, and many other thematic hubs in which this kind of work is underway. But what about the students which are studying at undergraduate level in different universities? So they should be convinced that the physics or the mathematical physics they are learning is also important in understanding and implementation of quantum computing, from quantum computing to quantum sensing in various ways. And that is what I would like to show here. So in this case, first task which I am going to show here is that mapping to the physics education. What are the things which we are teaching in our physics education can be employed for these kind of applications? So important topics are complex numbers, probability theory in the field of measurements, matrices, eigenvectors, tensor products, logic gates, optics, electromagnetism, solid state physics, classical mechanics. And the quantum principles which are being used in this are definition of the quantum states and phases, measurements, entanglement and multi-qubit states, unitary operators and quantum circuits, and many things related to the optics and photonics and also the superconductivity and Hamiltonian and time evolution. So this mapping of the physics, mapping to the physics education is already there. But only thing which we need to understand here is that in our classes, we can talk about these quantum computing revolution, connecting it to the topic which we are teaching in physics. And that I would like to demonstrate with few examples and trying to show that how physics classrooms can be used as a background for preparing our students for these kinds of applications which are happening and which will always be happening at a much faster rate in the forthcoming years. So here, the underlying contrast between a classical and a quantum state would always mean that classical states are deterministic states, whereas when we are talking about the quantum states, they exist in superposition of states with each state having some probability. And it is also important to know that the measuring the system will collapse the superposition state into one definite classical state. If I talk in this language, I think it will be very difficult for students to understand that what do we mean by it. So I would like to show that with the help of the following layout of the lecture, in which we are going to talk about qubits and its properties. What are the quantum gates? And when we are talking about quantum gates, what are unitary gates? And there will be three basic gates which I will be talking about, or four basic gates which are called the Pauli gates and also the Hadamard gate. These all are single qubit gates. But when we talk about a C0 gate, which is a 2-qubit gate, we will try to see that how it is implemented and how the mathematical formulation is also at the background of these gates. Why do we say that a thorough mathematical formulation is needed in order to understand these gates, which are otherwise called as quantum gates? And then on a quantum composer, students can make their own account with the help of a email ID and or other login details, and that give free access of say 10 minutes, but running these circuits takes only few seconds. So in that manner, if they have their own account, they can have a feel of these gates, and that interest may lead them to more understanding of these things. And another thing which I talked in the earlier slide, that this field is interdisciplinary. So there is a dedicated language which is called Python language in the form of Qiskit, which is a free downloadable software in which you can program, you can learn Python for this application. That is something would help in integration of mathematics, physics, and say computer science for these upcoming applications. So now, for students who are from school, I would like to, or otherwise undergraduate students also, it is very important to understand what is a classical bit. So when we are, everyone of you already knows that a switch is you know about the on and off the switch. It means that it is working, it is one, otherwise it is zero. In the terms of digital computation, we call it as 0 and 1 state. So in analog electronics, we in a very layman's language, we say when it is low or off, it is at 0 volt, and when it is high, it is at 5 volt. It can be like filling up of a tank, which tank is full, we say the state is 1. When the tank is empty, we say it to be a state 0. Same way, when we talk about a quantum bit, it is entirely different way of thinking when we are going to talk about quantum bit, which is in short called a Q bit. Q is coming from quantum and bit is coming from the unit for information. And when we are talking about quantum bit, its physical realization is held in terms of many different types of say physical methods, those are called superconducting qubits, neutral atoms, quantum dots, trapped ions, silicon, photons, NMR. All these are different kinds of qubits which are being talked about, or which are being which different people are working in order to have a scalable quantum computer. So I would request you not to go into these detail at this moment, but I wanted to tell this as a terminology that each kind of qubit is working on a different kind of a working principle. Their construction, their working principle differs from one to another. So we are not going to go into detail of this. What we are going to understand is that a quantum bit is a superposition of two states, which can be a 0 and 1 state. So if we take a coin, it is again an analogy. It is not the exact way of defining, but I think this analogy helps students to understand that what do we mean by superposition and what do we mean by a two-level system. So in this case, suppose we are having a tail and a head. I am representing the state tail as 0 and say state 1 as head. This everyone is familiar about. That is why I have taken this example. So whensoever I am coining, I am tossing a coin and it is in air. We can say that it is in a superposition state. As soon as it falls to the ground, then we say that it has acquired, there is a killing of its superposition and it acquires a stable state which is either 0 or 1. So let us see how does it look like. So if I say in terms of quantum, we can say that it is alpha times the state 0 plus beta times state 1, and that is the superposition state in which it is a combination of the say head and tail until the time my coin is spinning in air or it is being flipped in that particular form. It is in a state which is called superposition state, and as soon as it falls onto the ground, it is going to acquire either a head state or a tail state, which is the collapsing of the wave function in terms of the quantum mechanics. So probability of a coin landing in tails and the probability of a coin landing in head, these two for a unbiased coin. In case my coin is unbiased, would mean that there is a equal probability of the coin landing in tail or head. In that case, I can say that mod of alpha square plus beta square is 1, but that is also applicable when it is a unbiased coin. But what will happen in case it is a biased coin? Let us see that. So for a case of a unbiased coin, what is alpha and beta? If I am saying the probability for unbiased is equal, in that case, alpha and beta value will also come to be equal, and their total sum, that is alpha square plus beta square sum, is 1. So can you all write in the chat that what are the values for alpha and beta when we are having a unbiased coin? I would request students to please write in the chat that what would be the value of alpha and beta in case we are having a unbiased coin and the probability of occurrence of a head or tail is equal. So what would be and also we know that mod of alpha square plus mod of beta square is 1. So can I just request all the students to please write what will be the value of alpha and beta? Am I audible to everyone?
Yes,
And
madam.
how
Yes.
can I see my chat? I will just have to figure out that.
You can access the chat.
Yes, ma'am, I'm trying to do that. Just a moment. So this is my screen which is being presented, and in order to access the chat, I will have to look.
Just go down the taskbar.
Yeah, I have to press OK here, I think, and then I can access the chat. Yes, that is right. So may I request students to please write that what are the values of the alpha and beta in case the probabilities are equal and the coin has got equal probability of head and tail. So very well written that it will come out to be 1 by square root of 2. Very nice. I would request some more students to write, because our problem is now going to change, and let us see that what does it look like when we are going to say talk about a biased coin. So in the case of a biased coin, so for those who could not write in the chat, I would like to show it to them, that in that case, mod of alpha square plus mod of alpha square, because alpha and beta are equal, so that will be equal to 1. And in that case, alpha mod square plus beta mod square is half. So alpha and beta both are 1 by square root 2. But what would happen in case it is a biased coin? And then in that case, these values of alpha and beta will change. So let us see how does it look like. Suppose now we have got under root 2 by 5 times that I will be also introducing this ket and bra notation, but we can go without that also. So I am saying to under root 2 by 5 the state, which is my 0 state, plus under root 3 by 5 times my 1 state. So what is the probability of a head now, and do these values satisfy the normalization condition? So here it is very important to know that normalization condition would mean that mod of alpha square plus mod of beta square is 1. So in this particular case, can you check that the mod of alpha square and mod of beta square are going to be again 1 in case we are having, say, just a moment, I think I have missed that slide, just a moment. So if we are having values alpha and beta, say for the case when it is under root 2 by 5 and under root 3 by 5, so can everyone write that what are they following the normalization condition? Normalization condition would mean that mod of alpha square plus mod of beta square is equal to 1. Can you all write whether we are going to, is it going to follow the normalization condition or not? Yes, yes, yes. But is the probability of occurrence of head and tail equal in this case? It will not be equal. So one can figure out that the probability of both will not be equal, and that will be the case of a biased coin. So here we have introduced here the normalization. We have talked about the probabilities and how does the superposition occurring. Superposition would mean that both the states, the collapse states are the 0 and the 1 state, but till the time there is and I am emphasizing that it is just an analogy. In the real life, these are much difficult and complex, and these are facilitated by different types of qubits, which can be a superconducting qubit or ion trapped or a photon or a NMR. Different types of qubits are there on which everyone is working on to have a stability, coherence, a fast working time. All these are the challenges which scientists are and the engineers are struggling with in order to have a scalable quantum computer. So now further moving on, this concept is something which is also a part of, say, physics education, and that can be correlated with the quantum computing concepts. And that is what I wanted to show, that how the physics education can take care of the other kind of new revolutions which are occurring in terms of underlying the basics which are a part of these revolutions. Now, in the terms of a computational basis sets, we say that alpha times state 0 plus beta times state 1, which we are saying in the case again, a tail and a head. And that is how we define our say wave function. And now when we are talking about in the terms of vector or the matrix notation, we say alpha times state 0 is given by 1 and 0 in a column matrix, and beta times 0, 1. So if I don't know whether the class 11th and 12th students are basically they are capable of doing these kind of matrix multiplication at this stage, or they will be learning later, but I can just tell to them that it will become alpha times state 0 plus beta times state 1, and alpha and beta are going to be the defining factors whether they are going to be, these are nothing but which are representative of the amplitudes and the probabilities of the measuring of the wave functions in a zero state, that will be given by mod of alpha square, and the probability of measuring psi in a state 1, which is given by beta square. And in this is called a direct notation, and that is also taught in different mathematical physics and quantum say papers, which can be correlated with these kind of a say formalism. And now, why do we basically why do we have need to have a gate based implementation, and what are quantum gates and how these are different than different classical gates, and what are the basics which are required in order to understand the functioning of different quantum gates, and different hardware platforms implement these gates using various techniques, basically experimentally. And when we are talking about these gates can be applied using mirrors and beam splitters along with laser pulse sequences. So depending upon which gate or which mechanism we are talking about, there can be different understandings of that. But here, important thing to understand is that why do we have a unitary matrix in order to make these gates, and what is the role of the matrices multiplication or linear algebra here? So this operation can be linked with the basically matrix manipulation and the linear algebra, which I'll be showing just now. And there is a basic definition of a unitary matrix which says that it is when it is working, the psi prime is equal to u times the wave function which we are talking about psi. And for advanced students, those who are in the undergraduate and the postgraduate level, they are already aware of these matrix multiplication, and they know that u dagger comes out to be u dagger u is equal to identity vector. And there is a terminology which is used here which is called Hermitian, which is nothing but the complex conjugate transpose of a unitary matrix. And out of these identity, we also get that u dagger is equal to u inverse. So why do we need this kind of a thing in order to understand the quantum gates? Why is this need here? And that we will be just seeing in the forthcoming slides, and we will be seeing that why there is a need of a unitary matrix, and what do we mean by reversibility of a quantum say gate, and how does it work like. So when we are going to talk about the unitary matrix, as I just shown in my classes, we did some courses in that it can be integrated with Scilab or Python, that you ask them to write a state 0 and state 1 as a column matrix, and or as a row matrix in case it is being taken as a conjugate, and then they learn how to take the conjugate transpose of that. And then example quantum state can be 1 by root 2, which we just talked about, star state 0 plus 1 by square root 2 state 1, and then they can find different other operations with the help of Scilab or Python. And that is how they can understand that all these programming languages can be used to express different states, different operations, and that can also be an extended exercise in the classrooms. And then there is always other things like when we talk about the vectors and the tensors, inner product of state say 0 transposed and state 0, how does it show that when they are 1, when they are 0, that all can be also shown with the help of these kind of programming languages. So not going into detail into that right now, but I will be talking about the unitary matrix and how do we check whether a matrix is unitary, and what is its role in the quantum gates. So students, please see here that identity matrix is a combination of two rows and two columns when we are talking about in 2 dimension, and in that it can be written as 1 0 0 1. So it is an assembly of elements. So if I want to check that whether the examples of the following matrices are basically unitary or not, how would I do? If you go to the previous slide, we will take the complex conjugate and transpose it in order to see whether it comes out to be the unitary or not. So this is required for understanding of the gates, and that we will be doing one by one. So example of the unitary matrix and how do they satisfy the condition of the unitary condition, that is required to check the reversibility of gates, because reversibility of gates also plays a very important role. So let us see how does it look like. And in the IBM quantum composer, there is always also a requirement to understand the transformations from the Cartesian coordinate system to spherical polar coordinate system. And in that also we will see just now that in the quantum composer, how does it show the qubit in different states. So if I try to show here that this is called a block diagram, which is, I have taken this diagram, which is freely available in the Wikipedia as well as at many other places also. One can see that the qubit is initialized in a state 0. So this state 0 is the initialization of a qubit, and gate can be implemented on different states, and it can show probabilities in the case of in the case of probabilities in the percentage of the computational basis states, and it can show amplitudes of the computational basis states also, and it can show the state and the phase angle on the surface of a sphere. So one can show here this theta, this phi, and these are my Cartesian coordinates as x, y, and z. And one can always see that it is on a block diagram. It is represented in the form in the ways of r, theta, and phi, and that is also taught to a physics student in mathematical physics and quantum mechanics courses, and those are also needed in order to understand different states of the qubits, and that is what we will be seeing one by one in the forthcoming examples. So now the important single qubit gates are identity gate, X gate, Y gate, and Z gate, and the Hadamet gate. If I talk about this and just tell the name, I think nobody will understand that what do we mean by gates and why, what is the connection between the unitary matrix and these kind of gates. So let us delve into it slowly and slowly in the forthcoming slides. So if I say the poly X gate is a representation in the matrix form, which is 0, 1, 1, 0. And it changes the state 0 and state 1 to the corresponding some different states. How? Let us do that. If students have got pencil and pen, I will ask them to do, and if they are aware of the matrix multiplication, I will ask them to also do alongside so that they understand these things in more detail. Do we have some students who would be actually doing this alongside? Please say yes or no. Students do they have pencil and pen with them, and try to understand how we check about the unitary matrix and how what link they have got with the quantum gates. Do we have some students here? Please write yes or no in the chat. Yes, Raju has written yes, Diju has written yes. So okay. Okay, even if you can do it, that will be encouraging for others. So let us do that. So again, I'm going to the slideshow and doing it again. Okay. Can I use my pen here in order to show that? Turn on my pen here. Okay, that will be very easy for me to write here. So and students can do it with the help of Python also, and they can do it with the help of Scilab also, and they can do it manually also. So I am saying that I am expressing my gate X gate as poly X gate as 0, 1, 1, 0. It is working on state 0, 1. Okay, so those who know the matrix multiplication, they will get an answer to be 1, 0. How? We will multiply 0 with 0 and 1 with 1. So I will get 1 here. This is for those students who are not aware of the matrix multiplication and other concepts of linear algebra. I will tell them that in case I have got a 2 cross 2 matrix, so 2 cross 2 would means 2 rows and 2 columns we have. So it is called 2 cross 2. And in order to do a compatible multiplication, I am having a matrix which is 2 cross 1. And in case the column of this and row of these matches, then only multiplication can happen. So in this case, I will get an answer which will be 2 cross 1. So it will be like this, 2 rows and 1 column. And how does the multiplication take place? 0 into 0, okay, plus 1 into 1. So that will be my first element. So that will be 1, and 1 into 0 will be 0, plus 1 into 0 is again 0. So I will get here 0. Okay. So I will get 1, 0. So the poly X gate working on 0 state gives me 1 state. Is that clear? Because the 0 state is defined as 0, 1. Sorry, 1 state is defined as 0, 1, and 0th state is defined as 1, 0. So if this was my state 1, I am getting a state 0. And similar way, if it is working vice versa, if it is working on state 0, it will lead me to state 1. Can everyone check it? I can rub it and write it again in case anyone has not followed it, because if you do it for one, you should be able to do it for the rest of the states also. So let me just erase this. Just a moment. Erase all. So what did we do just now? That the poly X gate, if I am saying, is represented by 0, 1, 1, 0. It is working on state, say 0. State 0 is written as 1, 0. This is my state 0. So it is working on state 0, and the answer will come out to be 0, 1, which is state 1, and vice versa. If I take this state 1, 0, and it is working on state 0, 1, so can everyone write in the chat what will be the answer? If a poly X gate is working on this state, what will be my answer? Is my question mark. Undergraduate students will be able to do it very conveniently, and those in class 12 should also be able to do it. Yes, yes, very nice, very nice. Okay, so what poly X gate is doing? It is converting state 0 to state 1 and state 1 to state 0. Is that clear to everyone? I can erase again this all. Erase all. Okay. Now let us see what does it mean, and we will be trying to see its say through visualization also, and also in the IBM Composer. So what it is doing, the poly X gate is analogous to the NOT gate in the classical computing, and its action is to flip the state of the qubit. So if I say state 0 is nothing but 1, 0, and it will change the state 0 to state 1. So state 1 is nothing but 0, 1. So it is doing that task. Okay, let us go further. I will like to show this on the IBM Composer, that how does it look like, and how do we read on the IBM Composer is something which I would like to show it now. So let me do that. Just a moment. I can share my other screen also. I can take it a little bit down. Okay. And open the IBM Composer. Okay, this is a IBM Quantum Composer on which there is a assembly of gates on the left hand side, and this is the block sphere I talked about, and it gives us the probabilities in terms of the computational basis states, and it can also give us the state as well as the phase angle. All this is available to us when we are applying any gate and we are trying to see what happens to this. Can everyone tell me that on the block sphere, what is the initialization of the qubit? In which state the qubit is being initialized? I showed it in the block diagram a while ago. What is the state in which a qubit is being, initialized in a block sphere? It is the zero state. Is that clear to everyone? Is it visible to all? Please write yes or no. Yes, visible, right? Neeru Bhagat has written yes. Good. Others, please do write. In case it is not clear, please let me know. I will show again. Yes, Nilesh. So we can see that in the IBM Composer, the initial state of the qubit is zero state. Now we will apply a gate through this. Which gate? I'm going to apply a poly X gate, which is a analogous of the NOT gate in this. So before applying, let me again emphasize on the state in which we are applying. So is it visible that it is state 0 with probability 100? Is this visible? Is this visible? Yes. Okay. And what are the states which are possible in case of in the case of a classical one? It can be either a zero state or the one state. So right now it is in the state zero and probability is 100%. So it is like a classical. But when we apply this gate to it, this is a poly X gate. When I am applying it here, what happens? Can someone see the change here? What is now the state? State is now state 1. Is it clear? Yes, students. Is it clear? After applying the poly X gate, now the state is 1. Is it clear? Please write in the chat. Okay, very good. Very nice. Nilesh, Anish, Lekha, Manisha. Yes. Oh, sorry, Manisha ma'am. Anish, Digu. Okay, thank you so much. Okay. And can one see here that the state of the qubit kya hai? Pehle it was zero state. Now it is state 1. Is that visible in this block diagram? Is it visible after applying the X gate? Poly X gate, it is now in the 1 state. And what is the phase? How do we read the phase? Phase is given by this color. So blue color is phase 0. So it is blue color. And the phase, if the phase is magenta, that will reflect pi by 2. If it is red, it is pi. If it is orangish yellow, it is 3 pi by 4. Okay, so we can find out the state and the phase angle as well as the probabilities of different states. Now comes the question. Next question is, to this state, I apply another X gate. What will happen? To this state, I apply another poly X gate. What will happen now? Please write in the chat that what will happen if I am now applying another poly X gate to this state. Yes, Raju, ISRO has written zero state. It will come back to zero state. Anish, zero again. Fine, very good. Others, please do write. If I apply uh, another poly X gate, what will happen? So please let me apply now. So I will pull this NOT gate and drop it here. This is how IBM Composer works. So one can see that we are back to its original state. So any state, any matrix, which is any gate which we are experiencing or showing it here, if it is unitary in nature, double application of that gate will bring back to its original state. And that is demonstrated here. Is that clear to everyone? Is it clear? Yes. Okay, fine. Fine. Okay, so I go back to my slide again and try to see, understand further things. So I go back to my original slideshow and then we try to understand the rest of the gates. So still, this is a say image of the same thing which I have just shown in the composer so that I can show it here that the initialization in zero state and the probability in the zero state is 100% without the application of the gate, and then the amplitude for this is in the terms of state factor is 1, and when we apply the gate this happens. So this is a visual representation which I have taken from Luisha Gitbook.io, which shows that a visual representation which tells that if the qubit was in zero state, it is basically changes to state 1, and if it was in state 1, then it will go to state 0. This is what a poly X gate is doing. Is this clear to everyone? Should I move forward? Please write yes or no in that so that I know that otherwise I can re-emphasis on this once again. So please write. I'm checking the chat alongside, so that will help me to know that whether it has been conveyed or not conveyed. So these are very beautiful visualizations which tell you that what actually a particular gate is done. So right now we understood that what are unitary matrices, why we require unitary matrices, understanding in order to translate to the understanding of the gates, what are the quantum day gates actually doing, and we took an example of poly X gate. Now we go to the next case of it and try to see that what actually it is doing. And this also I have explained to you that if we apply it once, it is changing X gate working on state 0 will change the state to 1. Okay, and that is how it will look like in the IBM composer, and that is what, and if we apply it twice, then X gate working on X gate, like applying X gate twice on state 0 will give me X one state, and that will give me again back to the 0 state. So this is all which we have done until now. And next is my poly Z gate. Now my question would be, my Z matrix is 1, 0, 0, minus 1. I would like you to answer me that if it is applying on the 0 state, so I will write it here. I'm turning on my pen here. So my Z gate is 1, 0, 0 minus 1, and it is working on state 0. What is state 0? State 0 is 1, 0 state. 1, 0 in the terms of the matrix elements. So tell me that what will be the answer if the poly Z gate is working on the state 0, and what will be the answer when the poly Z gate will be working on state 1. So state 1 will be 1, 0, 0 minus 1 working on state 1. State 1 is 0, 1. So please write your answers in the chat for the first case first and then the second one. Right now, Anish, when we are talking about the particular functioning of a gate, we are talking about that what is in terms of it has got a fixed matrix elements, and we are just trying to see that what it is doing in terms of changing of the state. But when we will be needing arbitrary rotations, then there can be a combination of gates also, and there can be many other things in that. So right now we are just looking at the functioning of the basic polygates, which are 4 in number. First is the identity gate, and the rest 3 are X, Y, and Z gate. And we are trying to see that if a Z gate which works on the 0 state, what will be the answer, and what will be the answer if it is working on a 1 state. And then we will see that in the IBM composer, and we will see its visualization also in order to understand in more detail. Okay, so please students tell me what will be 1 0 0 minus 1 working on 1 0 and the other one also. So I'm getting answer as first case answer is 0. 0 state I assume you want to write, Anish, and second case is minus 1. So let us see what do we get. I can just show you with that. I can erase this and then we can try to see that what do we get. So can everyone see? And my students, when I took this class, though it is not a part of the syllabus, but when we are say doing basically different programming languages and we are doing different operations, so this thing can be practiced by the students as a extended example, or they can try to see that how can you write code also in Scilab or Python in order to implement this mathematically and using computers. So if you can see here, this is the poly Z gate representation. Working on 1 0 will give me 1 0, and if it is 0 1, it is giving me 0 minus 1. So what does it mean? What does it mean? That if it is working on this state, which is the 0 state, then nothing happens. But if it is working on one state, then there is a 0 minus 1. It means that there is a change in the state, which is basically the one state. So let us try to understand what does it mean. So it means that when it is the 0 state, nothing, it will remain as 0 state, but when it is the one state, it will become minus 1. Is this clear to everyone? Are we getting this from the previous example, previous calculation? That how does the Z gate work? That if it is having say 0 state, it remains same, but if it is working on one state, then it goes to minus 1. And in the IBM Composer, how does it look like? If it is working on 0 state, it remains the same, and it remains the same as 0 state. But if it is in the one state, here very important thing you will learn is that when it becomes minus 1, in the previous case, when we were talking about the poly X gate, when it was 1, the blue, it was the color of this dot, the state was blue only. So the phase was 0 only. But in this case, now the phase is also changed to pi, and that is what would mean by the minus 1 here, minus 1 state here. Is that okay? So this can always be taught as a extended exercises in the linear algebra, matrix multiplication, eigenvalues calculation, Euler's theorem when we are talking about, and we are talking about complex numbers and probabilities. These are also all are part of physics and mathematical physics papers. So this can be integrated with that till the time we get a full standalone paper which is talking about the quantum computing. So that paper has not been offered in, say, state and the central universities yet, as of which I know of. But in case these are offered, I think they can be, and they can be extension to what students are learning in physics and mathematics. Same way, there are other gates like poly Y gate, and these all formulations. Once you understand one, it will not be difficult for you to understand the rest of the mathematical formulations and rest of the things which are required in this. And another thing which I would like to mention here is that that we can always talk about the Hadamard gate. The Hadamard gate is the one which is representative of a superposition state. So what does it mean here? That I would like to demonstrate here. And here the matrix elements are 1 by root 2 is a prefactor, 1 1 1 minus 1, and it is useful for converting a 0 state or 1 state into a superposition state. So if we multiply by a Hadamard gate working on a 0 state or on a 1 state, it will yield a superposition state. So that we can also show here that by mathematically also, that if this is my representation of a Hadamard gate, if it is 1 1 1 minus 1, if it is working on state 0, I will get 1 by root 2 1 1. if you remember the previous state, only one state, zero state and one state. In that, one of the element is zero, but in the superposition state, both of these will have values. And in this case, it is 1 and 1. And in the case of if it is working on a one state, then we will get 1 and -1. And how will it look like? You can see here now that in the terms of probabilities, there is a 50% of the state 0 and 50% of the state 1 in terms of probability. And in the case of amplitudes, it will be 1 by under root 2. So it will be 0.707 and 0.707, because that p factor also was there. And now the qubit is in the 0 state as well as in the 1 state. And that is what we mean by the superposition state, and that is basically facilitated by the Hadamard gate. And same way, when we are talking about and because of the unitary matrix and reversibility of gates, you can see that if you apply 2 times, it will come back to its original state. So that is true for any kind of gate which we are going to talk about. Another example is the C0 gate, which is a 2-qubit gate. Again, students can do it as a Scilab problem also, and it can be done in Python also, and all multiplications can be done. One can try to see that this is a very important gate in terms of entanglement states and otherwise also. So it is a 2-qubit gate, and how does it work? It works in a manner that when the control is in 0 state, it does not do anything. And when the control is in the 1 state, then it applies the poly X gate on the target. This is how it works. And if I try to show it here, this is a representation of a C0 gate. And so in the case of 2-qubit, we will have different states. How the states will be now labeled in terms of computational basis states, it will be 0, 0, 0, 1, 1, 0, and 1, 1. And when it is being applied to say 0 state, so we will see that the amplitude is 1, and it is 0, 0 state is represented by this. And when it is being applied to one state, so one state is 1, 1 state, and before applying it to 1, 1 state, we have to apply another another poly X gate, because the initial state of the matrix of the qubit is 0 state. And if I want to apply any gate which is in one state, I need to apply a poly X gate, and after that I can apply the C0 gate. So one can see here the developed state now is 1, 1, and the phase is again can be noticed by this blue color. So there is a very beautiful way of understanding the theoretical concept using the IBM Composer, and then doing it using the computational programming languages. And then it can be basically one can write the code in Qiskit also, and that Qiskit can be I think for those who are interested in this, they can get back to me, or there are free tutorials available in order to understand Qiskit. So what is the difference between the IBM Composer and the Qiskit programming is that here we are pulling and we are basically taking one say gate and dropping it, and we are able to get the answer. When you write your own program, then you write a code, and that code will produce the kind of requirement of a gate or a application of a gate to a state. So that will be through a program. That is the difference between IBM Composer and the Qiskit, and that is what those who are doing advanced courses in these are learning as a part of their course. And normally these are at least 3 to 6 months courses, which can basically students can take. And these days many universities are offering these as add-on courses for those who are interested, as well as many certificate courses are available for those who are not being offered this as a part of their curriculum. And that is what students can learn, and they can they can be contributor for these say revolutionary advances which are happening in the field of these areas. And Bell states, when we talk about, their 2-qubit states are used, and there is a requirement for maximally entangled states. And when we talk about entanglement, everyone is aware of that. It is a state where the state of one qubit is correlated to the state of another qubit. So Bell states is something in which also involves the tensor product, which is also a part of physics and mathematics training. So I will not go into detail of this, but I would like to show you that this is the programming which is done using Qiskit, in which one writes a code and then call different libraries, and then one can generate these circuits. Instead of composer, these kind of circuits can be generated, and those can always be utilized for different applications. So these are there is a process for that. As I can see the diverse background of this. For some, it may be very, very difficult to understand. So, but I wanted to give a glimpses of it so that they can know that these kind of things are available in these kind of applications. And when we are using it in basically IBM Composer or a simulator, there is a possibility of basically simulating it without noise. So one can see that if a state is say in the 00 state, if it is a noiseless simulator, you get the full count as full count without any error. And here the concept of probability is very important, that these things are not done in 1 or 2 or 3 shots. A large number is taken, because probability is applicable not for say 5 or 10 shots. The number of shots has to be very significant, say 1,000, 2,000, and so on and so on. But when we introduce noise into it, because noise is playing a very, very crucial role in the performance of a quantum computer, because of the noise of the surrounding, noise of the say noise occurring because of the decoherence of the qubits, there are errors, and those errors may change the result. Like in case the state has to be in the 00 state with full probability, now there will be other states with some errors, and that is what is being dealt with in the case of quantum computing, that error correction or fault tolerant quantum computer are emerging, where the error can be say there are algorithms which can be written to reduce the error, and this has given rise to another new field which is called error correction and the fault tolerant quantum computers. And this has emerged as a new field of research in itself, and that is what people are working on. And so in summary, I can say that we had a look on the qubits, different types of qubits. We did not go into detail of that. We just talked about what kinds of qubits are available. Like IBM uses superconducting qubits, and in some countries people are working on ion trapped quantum computers. Also in India, in IUAC, they are working on ion trapped quantum computers. And I think a lot of infrastructure is being developed to tailor that to electron tapped quantum computer also, because of advantages. People are trying that. And from once we have qubits, then we try to make gates like the poly identity XYZ gate, which are single qubit gates, and followed by there can be 2-qubit, multi-qubit gates also, in which the complexity will keep on increasing. And quantum circuits are based on these qubits and gates. And working with IBM Composer, students can open their own account in that. They can play with the gates. But important thing to understand here is that what a particular gate is doing, they should first do that mathematically and through their computing language, so that they know that what is actually being done by that is understandable by the students, and then demonstration using Qiskit. So with that, I can say that these are the references which can be used by the students, IBM Quantum Composer and textbook. There is a very basic and very important textbook in this, which is Nielsen Chuang. That is a quantum computation and quantum communication textbook, which is called as a very significant book in this area. So with that, I can say thank you to everyone for your patient listening, and thanks for this opportunity to everyone. Thanks a lot. Any doubts, if are, please feel free to ask.
staff members or students, if you
Madam.
have any doubt, please raise. Yeah. Yeah.
Yes, madam. Good evening, madam.
Yes, can I just
This is
let
Dr.
me
Malia.
stop sharing? Yeah, let me just stop sharing so that I can get back to you. Just a moment, sir. Just a moment. Yes, you can keep on asking your question. I can just answer that. Just
Madam, very informative lectures on the qubits and the quantum information. Thank you. One of my
yes, sir.
questions regarding the how we will go for the experimental part. If I want to make a qubit in our laboratory, our setup, how can we do?
Sir, I think for qubit part, the National Quantum Mission has designated a certain amount of money to different thematic hubs where they are, say, having or developing different qubits based on different technologies, which I just said, superconducting and ion trap. All these are in experimental stage. At some places, wheresoever this has matured, they are giving an access, and so one has to get in touch with those where these facilities, because these are multi-crore facilities which are otherwise not available at the undergraduate level, but those who are having a hub or those who are having funding for these, they are working on it, and they can be accessed. That is why I think there has to be its penetration has to be there for undergraduate students also, as a part of outreach program or otherwise. As far as I am I am aware of these facilities, I think for undergraduate levels these are not freely available at this moment, and these are at developmental stage.
Thank you, madam. Thank you. Thank you very much.
Thanks a lot.
Vandana, there are some 3 comments in the chat box.
Okay, ma'am, I just checked that.
Control not get where it is used.
Yes, ma'am. I have answered the first one, and control
Baki, I
not
think they
get.
are just the
Yeah.
comments.
Control not gate is used basically for the creation of the bell states, and many other applications are based on that. Whensoever we are having, say, qubit interaction, at those places it can be when it is 2 qubit, then we are using these NOT gates, which is called C NOT gate, and otherwise there can be other combination of different gates as well. So in order to understand 2 qubit and multi-qubit gates, I think the basic will always go to single qubit, and then for 2 qubit interaction, tensor products and creation of the bell states, all these things first has to be learned mathematically, and then it can be done with actual, say, composer or with the help of other tools.
Yeah, very nice and very, as usual, it was a very
Thank you so much,
Ma'am,
ma'am.
in the
excellent lecture.
audience,
Yeah.
yeah, in the
Professor
audience,
Aluwalia has also joined.
always there. Yeah,
Thank you, sir. Thank you so much, sir. Thank you,
Aluwalia sir is
everyone.
also there. Sir,
he's there from actually he's there from the beginning.
yes,
So let
yes.
him express some
Okay, sir.
opinions.
Sir, your
Yes.
comments.
Yeah. Good evening to everyone.
Good evening, sir. Good evening.
And I'm very happy, ma'am. Vandana, thank you very much.
Thanks a
You
lot, sir.
accepted the request to come at a very short notice. I would like to tell the members and the students who are here, ma'am Vandana is a very dependable physicist. Whenever we have to really start new thing, she offers her expertise for doing all those things. Even in the ICP 2025 at IIT Ropar, she conducted a workshop on quantum computing itself. And I think that is a kind of a reason that when Professor Kanungude asked me, I said, look, I'll tell you, and she will do it. And she has done
Yes,
it.
thank you.
And she did it so systematically. I think that is a hallmark of her presentations. It's very
Yes.
cool presentation, and anybody can understand the things in a systematic fashion. I had a long association with Ma'am Vandana,
Thank you,
and
sir.
I
It's my
know her
privilege.
very much. And
Thank you so
we
much.
have, I think, today Professor Ghatak also present in this program. And I feel that I should really formally congratulate him on this occasion. Um, Professor Ghatak has got his name in Quantum 100, which was part of International Year of Quantum Science and Technology at the UNESCO level. Quantum 100 was an initiative in which this IYQ team wanted to identify 100 people who have contributed significantly to various aspects of uh, quantum mechanics, quantum science, quantum technology. And I think who can be a better person than Professor Ajoy Khatak in our country? I think generations have learned from him, and he is still, we are very blessed that he is still guiding us, helping us, making us learn things. And I think he is very inspiring when it comes to talking to students. Uh, I think very soon, maybe in the email, you will be finding a beautiful calendar which Sir has created for the new year, which has got Albert Einstein's quotes and beautiful pictures in that. And once again, I congratulate Professor Ajay Ghatak for being in this program and being part of our IYQ celebrations at IAPT also. Right from the beginning, in the month of January, when we started this set of lecture series, I think this is the final set of lecture series now going on. There were, for 8 months, we had wonderful lectures, and they turned out to be a very good compilation of uh, concepts of quantum mechanics and the history of quantum mechanics. So once again, I thank Professor Ghatak for being with us, and I also would like to say that this session is blessed because of his presence also. Thank you very
Yes,
much,
sir.
and thank you, Ma'am Vandana, and
Yes.
thank you, Ma'am Manisha, for initiating now activities at the Pune SRC08C.
Yes,
That is
sir.
just great.
Thank you.
So
And thanks
thank you
for the
very much.
opportunity. Thank you so much for the opportunity, sir. I'm also a learner in this field, and whatsoever I know, I can easily share. So thank you so much. And thank you, Professor Ghatak. One thing I want to tell about Professor Ghatak is that he delivered a talk in our college once and or twice. The human values he considered, I think, alongside whatsoever motivation and inspiration he gives, his re-emphasis or emphasis on the human values is something which I praise him for, other than the contributions which he has done in, I think, in multifarious ways. Thank you so much, sir. And Ma'am Rekha and Sir Aluwalia Sirji and all the team members who are there at the Pune, thank you so much for taking this initiative. And I think it will help the students. Only thing which I think is very important to underline here is that it should penetrate the state and the central universities in a big manner so that our students, undergraduate students, are not left behind. So that is what I would insist on. Thank you.
Yes, madam, sure.
Yeah.
Thanks a
Ma'am,
lot.
please go for formal vote of thanks.
Yeah. So, yes, I am proposing formal vote of thanks. Actually, this lecture is made so informal by Dr. Vandana, madam, that actually she told us about Dr. Ghatak sir also, and how she has followed his emphasis on human values, and that is seen actually in her lecture. So we are very thankful to Dr. Ghatak sir. Also, we congratulate him. Also, we are very much thankful to Dr. Aulwalia sir and Professor Rekha Ghorpade madam, and of course all the respected professors who have joined this lecture and was a part of this lecture. Also to all the students, I am very much thankful because they asked quality questions. They were very nice in their participation, as the lecture was very engaging. It was very interactive session, and once again, rather, it is proved that Vandana madam is a very nice teacher, because she could engage all of us actually for almost for 1 hour, 1.25 of the hour. So we also could have again, um, where we also could go to our college days or school days, and we did all those matrices calculations. So actually, madam, it was a very nice session, and
Thank
we also became learner for some time. No, actually, we have been throughout the life. Actually, as we are teachers, we are learners too, and it's actually very nice of you that you are again saying that you are the learner in this field. After achieving all these expertise, again, you are so humble and so down to earth, madam. We would like you to invite to Pune for taking the workshop, as Dr. Alwaria sir said that you took the workshop on quantum computing. So we would also like you to be in Pune and conduct such workshop. Soon we will be arranging that with the help of our EC members and with the state and central universities also. So thank you so much, ma'am, for this
Thanks a
wonderful
lot.
and interactive lecture. And madam, with a very short duration, on the very short notice, you accepted our request. So it was a privilege to us. Thank you so much. Thank you all.
Thank you so much, everyone, and all
Actually,
the
By the
students.
way,
I will suggest
by
Manisha madam,
yeah,
it is
Yeah,
not necessary to conduct an offline workshop, but even you
okay.
can go for online workshops so that more participants will have the benefit of it.
yeah.
And
That's
it
very
is,
big.
you can plan it in such a way that evening 1.5 hours, maybe three
Okay.
times a week. It can go for 2 weeks also. You
Okay.
have very resourceful people like Vandana, Mahesh Shetty, and all. I think they are already now busy with the winter school at Ratnagiri and
Yes, yes,
Kolhapur also. So,
yes, yes.
online workshop is more advisable so that Vandana
Yes,
can make it. We know
yes,
that she is very
yes,
busy and she never says no to anything.
yes, yes, yes,
Yes,
yes. He is a
Thank you so much.
yes.
hardcore teacher, a hardcore physicist, madam.
Hardcore teacher.
Yes,
Yes, yes.
yes, hardcore teacher. Yes,
Thank
yes.
you, Vandana. Thank you once
Thank you so
again.
much. Thank you, everyone. Thanks a lot.
So much, ma'am. Thank you. Thanks a
Thanks.
lot,
To all
and good night
respect,
to you.
yeah.
Thank you. Thank you.
Thanks a lot.
Invitation for the next Saturday. One more session will be there. A very young scientist
Yes.
from Qatar. He is actually
Mhm.
MI SPPO initiative in Qatar. Dr.
Mhm.
Vikas Kasit. He will be engaging this session, third session. That will be on
Mhm.
27th.